Hi everyone. Okay, let's get started. And welcome. First, I would really much to welcome and thank you for coming to this tutorial. So I am Hongyu, and together with Hanjun, Jiani, Ziyang, and Jure, we are super excited here today to present the tutorial complex reasoning over relational databases. And this tutorial will cover a broad range of topics about reasoning, representation learning, graph embeddings, and so on. Okay, let me first introduce our team. So my name is Hongyu. I'm currently a fifth-year PhD student at Stanford University, advised by Jure Leskovec.
Hi everyone, my name is Hanjun, and I'm from Google Brain, currently doing research in this domain.
Hello everyone, I'm Jiani, and I'm a fifth-year PhD student in UPenn. My advisor is Jure.
Hello everyone, my name is Ziyang, and I'm also a fourth-year PhD student in University of Pennsylvania, and my advisor is Jure.
Okay, cool. So as I said, right, we are super excited today to present this tutorial on reasoning over relational data. And you will cover 2 lines of work with hands-on tutorial on 2 code bases. So framework, basically it's called Smore and Scallop. So as an overview, right? So we first would very much like to introduce our data modality and also the task. So we are really interested in this type of heterogeneous relational graphs. So first, as a background, what is relational graphs, right? And a relational graph is a heterogeneous data structure defined over such a node set, edge set, and the relation set, right? And each edge on the graph is in this triplet format that captures the relationship between a subject and an object. So in the real world, examples of such data structure include scene graphs that capture relations between objects in an image, and for example, knowledge graphs that capture real world facts and knowledge about the world. And then what do we really mean by reasoning over such data structure, right? And here we categorize the literature along 2 axes. So on the vertical axis, we discuss whether the graph structure is actually given in a task, right? So for example, we have this type of implicit graph representation where graph is hidden and we only have this unstructured data as input. And we also have this type of explicit graph representation where we are explicitly given this graph structure as an input to the task. And on the horizontal axis, we discuss 2 paradigms of reasoning. First, symbolic reasoning really covers explicitly manipulating discrete symbols such as integers, Boolean variables, and strings. And usually such data used for symbolic reasoning is structured, right? And that's why we have this type of traditional database management systems. And basically this type of database management system may evaluate relational queries such as SQL to perform symbolic reasoning. And primary capabilities for relational queries include logical and or not, recursion for transitive closure, and aggregation for counting, summation, and so on, right? And with Scallop, we really demonstrate that explicit symbolic reasoning can actually be used to operate on unstructured data as well. And in this paradigm, we have underlying neural networks mapping the unstructured data to an explicit graph representation. And after that, we may apply differentiable symbolic reasoning on the graph using the Scallop framework. And since the whole pipeline is differentiable, the neural network may learn to extract very nice structured graph representation. And on the other hand, we also have neural reasoning, right? And such neural reasoning modules manipulate not on the discrete symbols, but rather neural embeddings, right? Which implicitly capture the semantics of entities and relationships on this graph. And neural reasoning modules thus perform this type of logic operations such as intersection, exists, quantification, all in the embedding space. And under this category, most methods may design their own neural operators to perform reasoning. And with Smore, we demonstrate that we can implement and scale different neural reasoning methods over explicit knowledge graphs that can operate over extremely large structured knowledge bases. And we do have also seen methods that perform neural reasoning over implicit graphs or unstructured data with some underlying graph structure. And this includes neural databases and neural algorithmic reasoner. But today's main focus will be to introduce Scallop and Smore and provide hands-on tutorial of the two frameworks. And we'll also include a discussion on the future steps of the two modules at the end. So with that being said, so here's our agenda. And we've also uploaded the materials to our website. So feel free to download it on our website with the link here. And we will also have the QA session together after introducing the two parts. And now I'm happy to hand it over to Ziyang, who will start the part one about the Scallop.
Hi, everyone. I'm Ziyang, and I'm here to present the first part of this tutorial, which talks about differentiable symbolic reasoning on implicit graphs. And in particular, we're going to discuss our tool, which is Scallop, a differentiable probabilistic reasoning language framework. So there are a lot of real-world data that are unstructured, right? Like, for example, we have natural language texts, images, and audios. And so shown on the screen, there are two examples. One is like a natural language passage. Inside of it, each sentence hinted at relationship between people. Like, for example, Rich's daughter, Christine, made dinner for her sister, Kim. As you can see, that there are these natural language texts are rarely natural, very natural, and but it actually captures some very well-structured data, which we can represent using graph and relational database representation. Right here, we can encode each person as a node or entities, and then entities are connected by their kinship relations, such as daughter and brother, and so on. And on the right-hand side, we can have like image as unstructured input. We can apply a bunch of neural networks to extract the entities or objects inside of this image, and then each object will become one entity in the graph. And there are relations that describe those entities, right? For example, we know the thing in the back is a tree, and there are two giraffes on the screen, and we can know that there are these two are giraffes, and they have some attributes such as tall, and we know the tree is green. And there are relations to connect different entities, right? We can have spatial relationships such as left, right. And in real life, there are many more very complex relations such as holding and talking or something like that. So the thing is that if we represent these unstructured input into the structured graph and relational database representation, it means that we can do very complex reasoning on it. So we could actually have neural components to transform these unstructured input to structured inputs, and thus learning the representation of the unstructured inputs. And then the discrete symbolic and logical reasoning engine, such as Dialog or Prolog, or any other logic programming systems, can be applied to such structured graphs. In this case, we actually care about deriving what is the relationship between Rich and Annie, who are implied in this paragraph. But let's say R and A, the relationship between R and A, they are not explicitly stated. So we want to do some reasoning to capture this relationship. And in particular, this task, we can frame it as a missing link prediction, because the graph representation only contains the edges explicitly mentioned in the passage, but then we want to infer some hidden edges inside of the graph too. Now, there are a bunch of advantages by doing this kind of discrete symbolic reasoning. Now, neural components and symbolic reasoning are disentangled, right? We now have separated responsibilities. Neural networks solely are responsible for processing these noisy inputs, handling ambiguities and such to produce this structured input. And on the other hand, we have discrete logic symbolic reasoners to perform the reasoning so that they are sound and exact, and then they can generalize better. They can support multi-hop reasoning, supporting constraint solving and things like that. So this is as contrary to like pure neural method, which directly takes in, let's say, natural language context and then predict the relationship between entities, right? Now, there are a bunch of challenges if we want to frame the problem into these two separate parts. How do we actually combine neural network with discrete symbolic reasoners, right? If without supervision on the intermediate graph, how do we train the underlying neural networks to actually predict the graph? And then on the right side, we have symbolic reasoner. How do we implement it? How do we, what if we do not want to specify all the logics to perform the logic reasoning, or can the learning system automatically infer the rules, or can it apply some constraints onto the graphs? So that is primarily the topics that we're going to talk about today. And the first one is we're going to talk about is differentiable symbolic reasoning. And next, we're going to talk about some extensions to differentiable symbolic reasoning systems that we use that can actually alleviate humans' effort to implement those symbolic reasoners, and also provide better generalizability and robustness to the model. Note that I want to note that here, although we are using this natural language task as a motivating example, it is actually very general, because a lot of data can be represented by graphs, and this can easily extend to many other tasks such as scene graph reasoning and so on. Yeah, right, that is our agenda. So first of all, we are going to talk about this differentiable reasoning. Traditionally, we have discrete graphs represented using deductive databases, or DDB. Here we represent a fact using a relation connecting entities. So in this case, we have B and R connected by the brother relationship, and then R and C connected by the daughter relationship, right? And the thing is that there are usually noisy input, and then it's very hard to extract those graph representation by like handcrafted rules. So we apply neural network to extract this. In particular, in this case, we are probably going to use some like large language models such as BERT-based models or LSTM-based models to extract those relations. For example, if let's say we are using those language models to extract those information or facts, they're probably going to predict some distributions over the relationship between two people, right? Let's say we are talking about this paragraph, and it has a bunch of entities. Between each pair of entities, we can use a language model to perform what's being called a relation extraction. And relation extraction will output a distribution of relations, right? So between B and R, they could be father, they could be brother, they could be sister, but then they will be associated with related probabilities, right? In this case, B and R is most likely Rich is Beth's brother, so that could be that fact could be tagged with a very large weight, while the other ones are tagged with very minimal weights, right? We can do that for every pair of people occurred in the unstructured input. And now, what do we mean by actually doing reasoning on this, right? So there are very commonly seen rules to do deductions. And here we're talking about rules as in Horn clauses, a subset of first order logic. So in fact, you can encode rules such as daughter's sister is daughter, right? This is a simple composition rule, and it is written in this manner. You can read it from right to left. So you say if A is B's, sorry, if B is A's daughter and then C is B's sister, then we can derive C is A's daughter, right? And in fact, we can execute this rule on the deductive database or the discrete database, and we can produce some proof tree like this. So on the top, we have the two facts being used to derive the fact on the bottom. In particular, we're talking about R's daughter is C, and then C's sister is K, and then we can derive K is R's daughter, right? Now, in order for this to be integrated with neural networks, we would need the facts being associated with probabilities. But then how do we actually propagate those weights and probabilities? And so that the result is also contains differentiable probabilities, so that the training pipeline is end-to-end. There are a series of work on this topic, and they are all forming into the differentiable deductive logic, differentiable logical reasoning paradigm. So the first work, just for reference, is called TensorLog. It's first presented in 2017. And in this case, the entities and relations are represented as vectors and matrices. And those vectors and matrices, they can be composed together by as simple as matrix multiplication. In fact, right here, if I want to derive who is Christine's sister, this rule is automatically compiled into a series of matrix multiplication. We have Christine being represented by a single vector, and then the sister relationship is represented as a matrix. At the end, we can derive another vector which represents who can be like the vector representing the variable x right here. So probably by this matrix multiplication, we can say that K is most likely Christine's sister. Now, this is equivalent to performing fuzzy logic, and there are many existing literature of fuzzy logic that we won't get into right here. Just keep in mind that this whole process is differentiable, and basically these discrete logic rules are turned into soft matrix and vector multiplications, so the whole pipeline is differentiable. And there's another line of work which is called dproblog. So this is another language for differentiable logic programming. And in this case, the facts and probabilities are not simply treated as vectors or matrices. Here, each fact is being treated as one discrete fact in a differentiable database, probabilistic database. And then there could be multiple worlds that derive the same result, although one of the world will be correct and the other would be incorrect. In this case, we can have daughter RC and sister CK deriving daughter RK, but then we can have like a, let's say, a incorrect fact being predicted by the neural network, which says C is our son, right? That is not correct, but the neural network could pretty much predict it, but maybe with low probability. And then that could be another world that help us derive the result of daughter RK. Now, to handle this multi-world semantics, they use something called exact probabilistic inference, and using process called weighted model counting. We won't get into details, but just keep in mind that all those processes are fully differentiable, and that means the final results probability, if there's gradient on it, we can backpropagate all the way into the input probability. Now we want to present our work, which is Scallop. It is a neurosymbolic language and framework generalizing all the previously shown engines, and it supports all those differentiable logical reasoning paradigms through provenance stammering. Again, we won't get into details because this is basically a hands-on tutorial. I just want to show like the high-level idea of how to use Scallop right here. And then Scallop is a language, and it's very general. It can be applied to many tasks, and we've shown it to be applied to domains including natural language, image processing, video processing, and things like that. But in this case, we are going to just talk about the natural language application. Here, Scallop is a language based on data log, and it naturally operates on graphs and deductive databases. It offers an easy-to-use PyTorch interface in order to be used along with existing neural models, and and in this tutorial, we're going to talk about some interesting use case of Scallop, which includes rule learning, inductive logic programming, and integrity constraint reasoning. So let's put this task concretely into a problem. So the user or the model is gets two inputs. The first one is a context, which is a natural language, And then the model also gets a query, which tells what is the relationship that we want to get from between two people. And internally, we want to have two models. One is neural network and one is symbolic reasoner. And the neural network is used to extract structured graphs from the unstructured input. And in this particular case, we would use and fine-tune a Roberta model, which is a large language model, to process the natural language context into the graph. And on the right-hand side, we have symbolic reasoner. We would manually craft a Scallop program as the symbolic reasoner for this task. And in particular, we're going to talk about some of the components of this Scallop program. So each logic rule like this, daughter's sister is daughter, is being turned into a higher order predicate called composition, right? Composition means you compose two relations and then derive another relation. In this case, we're composing daughter and sister, and that result is a daughter. And in fact, there are many other higher order predicate that you can define on this. A lot of, here we are showing three examples. One is composition, one is symmetric. Spouse is a symmetric relation. And then we also have transpose predicate, which says, for example, if B is A's wife, then B is A's husband. And by specifying these higher order predicates, we can define like our program just in like a few lines. This is one program written in Scallop, and let me go through some of the details. So first of all, we define some types. We have the query. The query is the question that the user asks, what is the relationship between subject and object? And then the kinship relation is what's being extracted by neural networks from the natural language texts, and it encodes a relationship between subject and object. Note that all of the facts under this relation would be probabilistic and differentiable. And now we define some constants, like we represent each of the relationship using some integers. And then we can define some composition rules, right? For example, daughter's sister is daughter. That is one of our examples. In fact, there are many other composition facts that we can input to this relation. And then what does it mean by actually performing the deduction in this database? It means that we have this rule, second last rule, saying if we have a composition rule R1, R2, and R3, and if we have X1 satisfying R1 relationship, YZ satisfying R2 relationship, then we have XZ satisfying the R3 relationship, right? And at the end, we would just want to get what is the relationship between the question, sorry, it should actually be query, sorry, this is a typo, should be the answer relation. Now, how can this, we just talked about this program containing a lot of compositions that the user manually specify, but in fact, they can be easily learned through a differentiable reasoning framework. And let's say we have this composition as a template. There are just a finite amount of relations. In this case, we have 20 kinship relations that consists of 8,000 possible composition facts. In fact, we can assign a learnable weight to each of those composition facts, and then just let the neural network learn what is the probable composition rule for among three relations. And at the end of the learning process, we should probably learn that the daughter's sister should be daughter, but not son or father or anything else. And this is represented by the weight being associated with this fact. And since they can be learned, the human doesn't need to specify all the rules by themselves, and they can just provide this template, and the engine will try to learn it for them. And there's also one other aspect of using explicit differentiable reasoning frameworks. So the graph extracted from by the neural networks from unstructured input could be ill-formed, right? So what if, let's say there are two people, John and Alice. We predicted that Alice is John's grandmother, but we also, the neural network also predicted John is Alice's aunt, right? That is certainly not a good, good prediction, and means some ill-formedness of the kinship graph. So what can be done in those in such a differentiable reasoning framework is that we can specify integrity constraint. This is a very traditional term in databases, database management, where we want to ensure the well-formedness of database systems. Here we are specifying one single integrity constraint. If A is B's grandmother, then B should be A's grandson or granddaughter, right? We can write that using a first order logic formula like this, and written in Scallop, we can have a rule like this, saying for all A, B, if A is B is A's grandmother, then that implies B should be A's grandson or granddaughter, right? So these are integrity constraints, and how do we actually use it to inform the to enforce the well-formedness of the predicted knowledge graph? So since we know that the input facts, the facts predicted by neural networks, they are associated with probabilities, we can just evaluate this integrity constraint and then get a probability for integrity constraint violation. And in this case, we treat this probability of violation as one loss, additional loss, which is called semantic loss. And in addition to getting the correct result, we want the differentiable reasoning system to also also generate this semantic loss. And in the optimization process, we should actually be able to minimize the semantic loss for training. And this can help us to learn a better representation of the unstructured input, which is a better graph. Now, putting it all together, like our model for natural language kinship reasoning has 4 components. The first component is graph representation extractor. It's based on some existing neural networks. And in this case, we actually use Roberta for it. And then we can have composition rules and their learnable weights. So there are 8,000 possible ones. And then we are, at the end, this system is able to learn a subset of those which are very likely true. And we can specify integrity constraints to ensure the well-formedness of the whole program, and then, of the predicted relational database. And lastly, we have one Scallop program to connect all these together. In the next part, we're going to talk about a demo, which will talk about how to actually use Scallop to combine all of these together. And let me first show some data, the data set stats and results. So in this case, we are comparing our model. On the left-hand side, we have this table comparing our model to some natural language processing models. And we can see that we can obtain significant improvement in accuracy. And also, we want to talk about one interesting topic, which is systematic generalizability. Let's say you have one very short natural language paragraph versus one very long natural language paragraph. And certainly the reasoning capability is the number of reasoning required to solve these two tasks would be different, right? We quantify this using the number of reasoning steps required. And in this data set, we actually have that number K to be from 2 to 10. And one of the interesting setup to test systematic generalizability is that for training data set, we only train on small examples, which are short paragraphs that you only need to derive a relation among, let's say, 3 people or 4 people. But then during testing, we're giving it very large context, and it might contain a lot of noise, and thus implying also longer context also implies longer reasoning steps, so that there we could have k equals to 2 to 10. And in this case, we can see that if we only train on k equals to 2 and 3 and then test it on more difficult problems, a lot of existing pure neural methods, they would suffer from a large drop in accuracy once they're fed more complex data. Then on our case, we have a perfectly generalizable symbolic reasoning system, and that can ensure the logical soundness and correctness of the reasoning result, given that the underlying graph being predicted is correct. So therefore, we can see that our line actually drops much slower than existing methods. Yeah, right. So there's one more experiment that we want to show, which is what if we don't have the unstructured input, and then we are just performing this kind of reasoning on structured input. And in this case, we would say the only task for the model to perform is to learn the composition rules. And based on this rule learning, our method would learn a bunch of actually 90 plus composition facts, and or let's say composition rules, and they are perfectly generalizable, and that can be seen right here as well. Our method could perform 98% accuracy, almost perfect. And this is compared to some traditional graph neural network model, which could suffer from not being trained on problems with more difficult setups. Right. Okay, I think let us get into the demo, and I'll pass on to Jiani to talk about some experiments.
If you just see this not shown image, you can just simply by signing in into your Google account to solve this issue. And after you signed in, you should see a page exactly like this. So hello everyone, I'm Jiani, and today I'm going to introduce how to use Scallop with PyTorch using an example of extracting a knowledge graph from data set. So the data set we're going to use in this lab is adapted from the Clutter data set, which is introduced already by Ziyang, a reading comprehension task. So this model should take in a story of a family's daily activity, a pair of family members, and generates the relationship between two family members. Just for simplicity in this specific lab, what we are going to focus on is just the reasoning process. We'll take in the graph that's representing the story, the graph here, introduce the relationship between the desired family members, which is shown in the query. So note that in this graph, all of the edges that are colored in black will be as a part of the input for our model, while everything that is colored, every edge that is colored in blue is a relationship that we can deduce from this black nodes. So there is actually a gap between deducing from these black edges to the blue edges, that is the composition rules, because you need to know, oh, daughter, sister should be another daughter. And this is a part of the composition we're going to learn from the data set. So starting from the environmental setup, we'll just first run the following script. You just click run anyway, and it will tell you the Python version of your Google Colab, and currently it is 3.8.16. This is the default setup I have used inside here for getting all of the required wheels. But if your Python version is a bit different from here, for example 3.7, don't worry, just use the link that we have presented in this note and you'll be fine. So what we'll do is just click here, it will install the Scallop, and it will download the mini data set that we'll work on. So yeah, I have already downloaded that, so it should be automatically done for you, but then we'll set up the whole training pipeline. There are some libraries that we need to import. There are some corresponding IDs to these relationships. There are something like called nothing. There is no relationship between, there's possibly no relationship between two persons in a story. It's fine. And then we'll build the data set, which takes in the raw data set and output a nicely formatted data points. It will contain a graph as the context, a name pair as the query, and the ground truth relationship between the two people as the white label. So after that, we can just set up the data loader with regards to this data set, and we can inspect the data point here. Just by running this, we can see, oh, Michael is Donald's father and Dorothy is Michael's sister. What is the relationship between Dorothy and Donald? And the answer should be ant. So this is just one simple example inside the data point, and we may just adjust your result and see another different pair of context. But note that the test and training data set, they have very different difficulty. If you see the first example in the test data set, what you will see is the context is pretty long. If you want to deduce the relationship between Evelyn and Lisa, you need to look at all of these parts inside the context, and finally you can deduce the result. So it essentially means the test data set is much harder than the training data set. And we can see the neural model after this. So the neural model is here. Essentially, we first have we have one learning component. It is the compositional rule. That is, for example, mother's mother is grandmother. It also includes these incorrect ones, like mother's mother is sister. But at the end, during the learning process, these will just have a low weight, and we will not include that. It will not have great impact on the finally deduced results. And the Scallop program used in this model just consists of the following 3 rules. We'll say, oh, if a relationship exists in the context, then it is a derived result. And if there are 2 relationships that can be composed using a composition rule, then they're also derived. And we'll query for the answer for the subject and object, and we'll see what are the relationships derived between the subject and objects, and we can obtain this answer. So here is the model itself. We first initialized all possible composition rules in the form of a triplet. And then we'll keep record of what are the probabilities corresponding to all of these tuples by initializing it with a fairly low probability. And we'll see, it is something like probably lower than 0.1 for each of the probability as the initial starting point. For the Scallop part, it is basically everything here. So we'll first create a Scallop context, declare relations and their types, add the rules as we mentioned here, and then we'll set some configurations of something which are not probabilistic. And finally, we'll have the forward function that is say, map the final result, which have the relationship of answer and map it into a range, map it into a vector that is of dimension 20. Inside the forwarding function, what we'll see is we just simply first obtain a list of tuples, which are probability and relation pairs for the composition tuples. And then we simply run Scallop to reason about the resulting relations, which is we'll just input the context tuples, put in the compositional relationships, and put in the question here. And the result will automatically be a vector of dimension 20. And the whole process will return us the result of what are the probability of the relationships between two curate person. And we have more complex version of the clutter model, but we'll come back to it a little bit later. So in terms of the trainer setup, no adjustments are required to just incorporate Scallop with just an ordinary trainer. You will just set it up as usual, keep logging the progress stats, putting the forward and backward propagations as usual, and we can run the experiments. We'll have set up some learning rate and device, blah, 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 and we can train it. Now that the training process has taken place, it will take around 3 minutes to run. So we can just take a look at the previous part, the model we have just skipped. So as Ziyang has just talked about, this model may not only include the function of just learning the compositional rules, but instead it can perform a bunch of different aspects, such as relation extraction, rule learning, and integrity constraints. Let's take a look at the code. So in this case, we have incorporated a relation extractor, which is based on Roberta. And we have also incorporated an MLP classifier that takes in the embedding from the Roberta and produce the relationship between the two names inside one piece of the context. Also, we have the compositional probability set up here. And we have an extra part of the integrity constraints. In this case, the integrity constraint says there is the father, if A is B's father, then it implies B is A's either daughter or son. Similarly, we have if A is B's grandmother, it essentially implies B is A's granddaughter or grandson. So anything that's not satisfying these integrity constraints will have a corresponding probability, and we will try to suppress this this integrity violation loss. So in this case, we will in the forwarding function, we'll set two parts. One part is also the answer, what is the answer corresponding to the question, and the other is the integrity violation, does the integrity violation occurs. We have the code for how do we extract the relations. There are some techniques to obtain the embeddings. Plus there are like further things to build on to extract these facts. And in the forwarding function, what we'll see is we have a part which is pre-processing the context, extract the relations, and extract the facts. This is something in addition to the previous model, and this is similar for the composition relations. And after we execute the reasoning process, we'll obtain both the answer and the semantic loss. And we'll return the final result as a pair of predicted answer and semantic loss, and both of these can be used in the loss engineering process. Since this part is pretty complicated, as you can see, it will take some time for training, and we will not run it in this lab, but you kind of can grasp the idea about it can incorporate these functions together. Now let's take a look at, okay, it is almost done here, and let us wait for a while, and we can see what are the rules that we can obtain from this learning process. Yep. If anyone have some setup questions or issues with regard to running this piece of code, please let me know in the chat box, and I'm very happy to help you out. Okay, now we have, after just running one training epoch, we have already achieved pretty high accuracy in the testing epoch. And what we can see is there are a few rules we have learned from this training process. It is saying one's brother's grandmother is also one's grandmother. And the grandson of a husband is also a grandson of the one. A sister of a sister is also a sister, and wife's daughter is your daughter, blah, blah, blah. So these rules are pretty sensible by the learning process. And I will put the share screen back to Ziyang, and that is basically it for demo. Can you explain the training output? Yeah, sure. So the training outputs here for the get rules is essentially I have taken out all of the probabilities corresponding to the tuples. So if you can see, here is the probabilities, and each of the probabilities actually have a corresponding composition tuplet. And they are among the 8,000 possible 8,000 possible tuplets from, for example, mother's mother is still a mother. These ones can be wrong. However, after the training process, we will encourage the one which are used in obtaining the correct outcome. And in that sense, we can encourage the probability of the correct compositional rules. So in this case, we can obtain the rules that are learned just by setting a threshold of 0.6 right here.
Hello. So I'm going to wrap up this first part. So basically, in this first part, we have discussed Scallop, our differentiable symbolic reasoning engine, and then we discussed how complex reasoning are performed, for example, performing deductions and learning rules, and then applying integrity constraints to ensure the graph's integrity or well-formedness as predicted by the underlying neural networks, in this case, a language model. Certainly, this method can be applied to many other domains, such as image processing and so on. Here's our website. We have a language called Scallop, and the website is scalloplane.github.io. And I'm going to pass on to Hongyu to discuss the second part, which is Smore.
Okay, so in this part, I will present Smore, and we really think about how to tell the other side of the aspect of the reasoning framework, right? It's really like we think about how to do neural reasoning over an explicitly given graph, right? And that is the biggest difference between our setup and the setup of Scallop. So, and let's first discuss the reasoning task, right? So reasoning over such graphs includes basically answering this type of acyclic, multi-hop complex queries, which is like a subset of first-order logic that has this existential quantification and conjunction, all of these logical operators, right? And one example we can ask over the graph, the given graph is that, for example, like where did all Canadian citizens with Turing work graduate? We can first convert this natural language question to this logical formula as shown below. And we can actually also represent this query with a graph, right? And it is easy to see that such queries have a tree-structured query plan or this query graph, where the leaves represent the topic entities mentioned in the query, and this unique root node represents the answer, right? And we may simply execute this query plan symbolically on the knowledge graph, right? So first we start with the Turing world in Canada, we traverse by relation winner of and citizen respectively, and get a set of Turing world winners and Canadian citizens, and then we take the intersection of the two sets, and finally traverse again by the relation graduate from to finally get all the answers to this query by symbolically traversing or executing this query on this knowledge graph. And such a task really has a wide application in many downstream domains, right? For example, in biomedicine, we can ask such a query on a biomedical knowledge graph, which may further accelerate the process of drug discovery by suggesting the most promising missing facts, right? However, when we really make predictions on the real world relational databases, right? As I introduced in the previous slides. This type of knowledge graphs are often really incomplete in the sense that there are many missing data and missing relations, right? For example, like on Freebase, which is like a really common and really popular knowledge base, is that 93.8% of people from Freebase even have no place of birth, right? And 78.5% have no nationality. So these are really like imposes a huge challenge of the current like symbolic algorithms. And thus we really require like a robust neural reasoning method to reason over such like noisy and unobserved data structure. Yeah, so inspired by embedding-based methods, right? Our general neural-based idea is that we can embed all these entities, all the nodes and relations, entities and relations in the shared embedding space, right? And we also would like to reason in the same embedding space. And what do I really mean by reasoning in that embedding space? So by this, I mean that we also want to embed this query in the same latent space. And then we can, the benefit is that we can easily find the answers to this query by a simple nearest neighbor search, right? We just check which entity is close to this query embedding in the embedding space, right? And we may simply train such a model using contrastive learning, optimizing the distance between the query and then an entity, right? And this will result in a low-dimensional embedding that is like that really allows for this type of like generalization and is like very robust to missing information. And the natural next question is that how do we even embed the query, right? How do we do this type of like neural symbolic representation learning? And our idea is that in order to embed the query, we can simply embed it by following the query plan. Since this query plan really exactly corresponds to the reasoning process, right? So in detail, we simply traverse the query plan from the leaves to the root, just exactly like what I just introduced, like how we do this reasoning process. But then the difference is that we don't symbolically traverse on the knowledge space, but rather we traverse it in the embedding space, doing this type of neural reasoning. And later I will show an example in the following slide. And here I will really like to introduce our model. It's like query to box. And so in query to box, we represent each entity as a single point vector in the Euclidean space. And each query we represented as a hyperrectangle with two sets of parameters. One high-dimensional parameter corresponds to the center of this query hyperrectangle, and another high-dimensional vector corresponds to the offset of this box. So this is really inspired by the previous work, probabilistic embedding of knowledge graph with box lattice measures. But in their work, they try to use the box embedding to model the ontology of a knowledge base. But here we use the box to really embed the query and to model the neural reasoning process. So yeah, so researcher box embedding is very natural, right? To model this query as such a hyperrectangle, and it naturally has this property of volume or size, right? That corresponds to the complexity of this query or the number of answers a query has. And many logical operators, such as like conjunction, can be naturally calculated over the boxes. So here is one example of query to box, right? So we are given this input natural language question, but really we can convert it to like some logical structure formula and this query plan that corresponds to the reasoning process of this query, right? So we start with an embedding of the Turing world and Canada. And since they are only like a single entity, we embed them as a single point in the Euclidean space. And then we project this single point to a box based on the relation winner of and the relation citizen following this query plan. And we may achieve the box that represents this red box represents the Turing world winners, and the yellow box represents the Canadian citizens, right? And then we can take the intersection of the two boxes, which corresponds to taking the intersection of the two sets, right? And finally, we may project the intersected box to the green box, which is the embedding of this whole query. And we hope that the answers to the query lies in the green box. And one thing I would like to highlight here is that we only do the decoding, like find what are the entities inside the box in the final step. Like we do not need to really decode the red box. Like we do not need to really find who are the Turing world winners. We just represent this set using a neural representation, which is this red box. So Query Toolbox really shares the benefits of all the embedding-based methods, right? Specifically, we can embed any query really efficiently with like linear computation time, right, with respect to the query size. And we can really obtain the answers in a scalable manner, basically by a k-nearest neighbor search. And the whole design choice makes sure that the Query Toolbox is also very general, since we do not really even limit the query structure. And in theory, Query Toolbox such a model can deal with query of any structure and size. And the reason is that we design all the neurological operators, no matter it's like the relational projection or the conjunction, they are all trainable by design, right? And they are all closed operation, right? So the projection operator takes one box as input and outputs another box, or the intersection operator takes multiple boxes as input and output a single box, right? So if you can see that all the input are boxes and the output are boxes, right? So they are naturally trainable. And finally, since we reason completely in the embedding space, so the model is very robust to noises, and especially it can deal with graphs that has missing and noisy relationships. And there are like multiple existing methods that also develop like different geometries using different architectures to solve the problem. And here's really like an incomplete list of methods for this task. And this includes like query embeddings, which follows the same framework that I just described, right? So we traverse the tree structure query plan and gradually perform this neurosymbolic reasoning and embed the query. And there are also like a broader range of other methods. Some like use neural link predictors and use different architectures like transformers, like graph neural networks, and even fuzzy logic. And what I want to say here is how to develop like more expressive and better query reasoning methods, these neurosymbolic reasoning methods over this given explicit knowledge graph is an active research topic with many, many open problems and questions. However, the goal here, right, is really that we want to scale such algorithms up to like extremely large knowledge bases, right? For example, to Freebase with like roughly 90 million, 86 million nodes, right? And the challenges of scaling up Query Toolbox or this multi-hop reasoning algorithms is really that from the algorithm side, right? In order to perform this self-supervised training, we need to construct this mini batch that include like a complex query, one positive answer and several negative answers, right? And we have to sample such data online, right? Since we cannot no longer pre-generate a set of query answers offline before training, because like there are exponential number of complex query on this large graph. So we perform the query sampling or generation from a top-down fashion in the sense that we first instantiate the root node of the query plan, and we do this type of instantiation in a top-down manner until we instantiate all the leaves of the query plan, so that we can guarantee that the sampled query have answers. And next, we do this type of answer and answer sampling using a novel bidirectional sampling that reduces the complexity by square root compared with a naive exhaustive traversal-based methods. And later in the demo, we will show that it is really efficient. And another challenge is really on the system level, right? So our framework designs a distributed training paradigm where we store the sparse matrix, sparse entity embedding matrix on the shared memory and the dense parameters on each device, for example, like one GPU. And then for each worker, we repeat the following procedures, including like sample mini batch of query answers, load the relevant entity embeddings from CPU to GPU, and then do forward query embedding and backward gradient calculation. And for the sparse embedding matrix, you update the shared embedding matrix in an asynchronized manner. And for the dense parameters, we do like this all reduce for the gradient and update in a synchronized version. So overall, we introduce this Smore, which is the first framework that scales all these multi-hop or neural reasoning algorithms to extremely large knowledge bases. And besides, we also design like a structured pipeline for training, right? Where we can have as much overlap as possible for all the 4 procedures I just mentioned that each worker needs to repeatedly finish. And to reach the goal, we design like multi-thread bidirectional sampler with this prefetching mechanism. And also we have this sparse embedding to pin memory to GPU communication. And overall, our framework Smore supports like 6 different knowledge graph, link prediction, and multi-hop reasoning methods, where while prior implementation runs out of GPU memory and time limit on performing this type of like neural reasoning task over large knowledge bases, our Smore framework achieves like almost graph size agnostic speed and GPU memory usage, right? So if you check the figure here, we can show that for the 3 listed graphs that has like drastically like orders of magnitude different size, we show that using our Smore framework training on different graph size, basically use the same speed, similar speed, and also similar GPU memory usage. And also like Smore also enables almost like linear multiple GPU speed up. Right. So, and as I said, how to develop this type of like more expressive, better query reasoning method is really an active research topic. So with Smore, we have an extremely modularized implementation where like really implementing a new method only takes like less than like 100 lines of code. So here's I would really like to hand it over to Hanjun, which will show a quick demo of Smore.
Oh, yeah. So once you open the page, you can we will demo using a GPU-enabled environment. To do that, to click on this edit and the notebook setting, you will see there's a hardware accelerator selection. And if you can, please use GPU. But if you cannot, you can safely use the CPU only. And based on your selection, you can check whether you use GPU or not in this checkbox. And remember to connect to the your machine. And after that, just run the several the first several execution series. Basically, it's just install a set of dependencies and after that, you can safely install the pre-built wheel from this website. I think it should work, but just in case if it doesn't work, you can just safely rebuild, uncomment this code and rebuild it from source. But I think it should work directly. So just run this there, and it will install the Smore package for you. And after that is done, you can see if you can safely import the Smore. Okay, I will give it maybe 1 minute to for setup. Okay, while we're waiting, I will just briefly cover what we're going on in this tutorial. So we'll cover mainly these 3 sections. Firstly, is about suppose you have your own knowledge graph. How can we load that into Smore and play with it? And secondly, as Hongyu mentioned, this Smore contains not only about the knowledge graph embedding models, but also like an efficient sampler that can sample multi-hop queries to train your knowledge graph. So we also demo how we can efficient sample from this knowledge graph. And the last part is after you set up all this interface, how can you hook your own model into the Smore and run your own model against the existing benchmark or your own knowledge graph. So that will be the agenda for today demo. Okay, yeah, so let's go from firstly, let's just download the knowledge graph from this website. And this is a pretty small knowledge graph. After that, Smore comes with this kgmem class, which is basically just a memory holder for the knowledge graph. And to instantiate a knowledge graph, you can first point your memory object to this binary file that is already pre-processed. And the reason to do that is we hope to load the knowledge graph very efficiently, like maybe the knowledge graph with billions of nodes, for example. After that, you can create a shallow copy of that. This enables that you can, for example, run multiple processes by linking your knowledge graph object to the same memory piece, so that it can safely run multiprocessing jobs without increasing the memory usage. Yeah, after that, you can see this is a pretty small knowledge graph with just this many nodes or entities. This is mainly for demonstration purpose. After that, this knowledge graph object itself is very handy. You can safely to query it. For example, here I specify whether there existed a edge between this head entity and tail entity with this specific relationship. You can simply run it and it says true. Yeah, it indeed contains this kind of edges. So if you want to develop your own sampler or anything like that, you can safely reuse the knowledge graph interface. It is efficient in terms of handling the large scale knowledge graph. So that's why we rebuild it in the small package. I can take a quick question maybe. The entities in the knowledge graph also have labels, test. Yeah, right now we just, in this demo, they're just integers, but we also enable the featureized representation of entities or relations. That will be not covered in this tutorial due to the time limit, but we have that in the GitHub page. Thank you. Okay, yeah, so next we can, yeah, thanks. Yeah, next we can see how we can sample from this knowledge graph with especially handling the multi-hop queries. We run this and it will import this so-called online sampler that we just build it by default. You can also build your own sampler, of course. The following block is trying to instantiate a sampler. What you need to specify are this set of parameters. So in knowledge graph training, we typically do this contrastive learning where you need to specify the positive entities and also the negative entities. So in that case, you need to specify the number of samples to be inactive. And also, we have different types of samplers that you can try. This naive version would just exhaustively explore the knowledge graph to get the positive and the negative example for your query. And the query template here is we already make a short name for it. You can check our paper or the tutorial to see the meaning of it. The specific this query structure we are going to use is a two-hop query where it contains two relations and one entity. The physical meaning is asking, for example, who is graduated from a city that is located in US, for example. So there are two hop questions. So, okay, after that, we're pretty much done with the specification of the sampler. So you can safely check the sampler. Let's run this basic version, and you should see this progress bar. Although it is called a naive sampler, but it's still relatively efficient because we rewrite everything in C++. So, and also it supports the multi-thread sampling. You can specify the number of threads here to make it even faster. Yeah, and as we mentioned, in the small package, we developed a new sampler that has this theoretical cost that is supposed to be just a square root of the naive one. You can reinitialize another sampler and safely run this. Yeah, and after that, it takes shorter time, but for this small knowledge graph, the difference is not significant. If you are interested in trying more, you can safely download another larger knowledge graph from OGB. And this one has millions of entities and tens of millions of edges. So you would be able to easily see the difference when you rerun the above series. Due to the time, we will not run this again, but if you're interested, you can safely uncomment this code and run it again. Okay, let's see what we actually sampled. This is what the sampler would return. I will explain it briefly. So it will return a set of positive entities and a set of negative entities. And for each positive entity and negative entity pair, we also return a binary matrix indicated that whether it is pair of entities is really a contrastive example or not. So and the weight and that would be fine. The one thing I want to cover is this the structure of the batch, the query it returns. So previously we specified this this query should be a two-hop query, and here is an instantiation of that query, which means we start from this entity of this index, and it should take two relations with indexed by these integers. And that is basically the structure of the query. And yeah, after that, we are ready to build new models. Okay, so after we introduce how you can sample queries, then you can basically treat it as a black box and only like take this as a high-level interface. And once what you need to think about is once we get the positive examples and negative examples, how you can build a knowledge graph engine, like reasoning engine to reason about this multi-hop query and to give higher score to the positive entities and lower score to the negative entities. And here we simply use this very basic reasoning, multi-hop reasoning as the illustration. So it would inherit from this generic class called KG reasoning. You definitely need to specify some hyperparameters like a number of entities, number of relations that would be involved, because here we have a embedding matrix that is dependent on the number of entities. But you can also like develop other model that doesn't depend on it. So this very basic model would only be able to do the multi-hop relation projection, which means you can have a two-hop or three-hop query that only contains the relation projection. So in this case, the relation projection is simply just a summation of two embeddings, for example. And then you also need to specify how to calculate the logic. So basically saying that give you the embeddings, how you can convert that into a scalar that indicates the unnormalized score of your confidence on this fact. And you can simply run this and then create this model. This model will only be able to handle this two-hop query, as I mentioned, like it specifies the entity relation. And after that, you just do the forward, and we already handle how to handle in the generic KG reasoning class. We already know how to handle different types of reasoning, so you can simply just put this and run it. And after that, the loss function is kind of generic, but you can also develop your own one to say give higher score on the positive entities and then lower score on the negative answers. And here's the loss. After that, you can just take a gradient back and after your parameters. I will not cover that, but hopefully that will be straightforward from here. Yeah, the last part is about how to make it a slightly bit more intelligent. So how to enable it to handle the intersections of the two queries. That will be the part that we're gonna demonstrate in the end. So in this part, we still inherit from this very basic version of our knowledge graph reasoning module that we just defined. And we need to additionally define the neural network that can handle the projection of intersection semantics. In this case, we simply reuse the intersection module from the query to box Hongyu just presented. I will not dive too much into detail. This is mostly just a design choice. And all you need to do is to specify how you can give you two sets of embedding, how you can do intersection operator in your case. And let's build it again. And here we try another query template where basically you need to intersect between two, for example, in box representation, you can try to do intersection between two boxes, or in our case, we just do intersection between whatever embedding we just obtained. Because we have a new query, then we can build a new sampler for it. And also sample the corresponding positive and negative examples. And after that, we are pretty much done with this slightly advanced module. Yeah, so that is just a very quick and high-level introduction to the Smore, but basically cover all major components: the sampler, the knowledge graph representation, and how to cover your own new model. There are definitely many advanced topics, and especially like we offer the opportunity to write your own efficient CUDA or C++ kernels for your own like knowledge graph embedding techniques. And also, as a question raised in the chat room, we also enable how to use the featureizer representation for those entities, and to make it more representative and increase model capacity in this case. And for more information, please feel free to reach out to this GitHub page, or feel free to send us an email if you have pull request or any question or anything you want to discuss. Yeah, that's it. I'll give back to Hongyu.
So this concludes like our part 2, where we introduce like a box embedding for this neural reasoning over the knowledge bases. And we also present Smore, which is like efficient and scalable framework for implementing all these query embeddings to reason over these massive KGs. Then as a final remark and future works, so we basically here in this tutorial, we present 2 frameworks. One is Scallop, that is like a differentiable probabilistic symbolic reasoning engine, and it allows deep integration with existing neural networks for extracting structured relational database from unstructured input. I've also proposed Smore, which is a framework for neural reasoning over graphs and relational databases, and it allows for complex multi-hop reasoning, and it can easily scale to extremely large knowledge graphs. And together, right? So for future works, we really think about the problem, whether we can combine the best of both worlds, right? And design like a reasoning framework that is capable of handling both discrete and embedding-based relational symbols, and it's also scalable to large and noisy knowledge bases while retaining the logical soundness and completeness, right? And this may really require like disruptive and paradigm-shifting innovations. And another open problem here is to also think about how to grant this type of logic reasoning capabilities rigor to like large language models, for example, right? Can our frameworks help with the reasoning capabilities of LLMs? And can LLMs in turn help increase the reasoning power or expressiveness in the setup or in the context of reasoning over graph databases? So yeah, thank you guys so much for coming to this tutorial, and I hope you guys learn a lot how to learn a lot about the reasoning task and also the 2 frameworks. Yeah, thank you so much, and please let us know if you have any questions.
Yeah, so while we are waiting for the questions, so I see a comment in the chat room, the Slack, and someone asked about the slides and the code, and we will share it in our website, where we can also paste it here. All the content will be available here, and the 2 collab tutorials are already put on the website. Okay, there's a question in the chat from Mutun. He's asking about, do you have any hypotheses of use cases in maps like Google Maps or Apple Maps?
For applications on maps, I assume they are like the applications I can think of are like predicting the routes, right? The routes or the estimated time of arrival, or even have some recommendations, right? So I think like this type of like reasoning algorithm may definitely help like in these applications, especially for like recommendations, right? We may even like ask queries like recommending some restaurants like with some constraints, right? With some logical constraints. Then I guess like our methods really allows for perform such reasoning over this like fuzzy graphs that we can construct from the maps, from Google Maps or Apple Maps.
Yeah, I think I want to comment that maybe Ziyang, you can cover more, is the Scallop package actually enables you to put logical rules like transactive rules, and you can easily specify the shortest path algorithm in it. So if you think about it, you want to navigate on the maps, if you how to incorporate that knowledge into your neural network and allow, say, doing shortest path or connectivity reasoning, that is also possible. And I think Ziyang, you have the Scallop has another good example for that, if you want to cover it.
Yeah, thanks, Hanjun. Yeah, great. So Scallop is a general language, and it's very easy to specify a lot of seemingly discrete algorithms inside of this language. Certainly, there are like shortest path finding programs in logic programming that is very well known, and then we can easily implement that. And then, so the thing is that like all of those predictions, either embeddings or probabilities, they can be associated as tags in Scallop. So we can easily propagate those to get any result. So yeah, it would be nice to incorporate some logic rules, discrete logic rules, especially interpretable and explainable by human, and integrate that into like any kind of learning system. Yeah, and I think for both of our works will support some sort of it. Yeah.
Just thinking of some more concrete examples, it could be going through multiple destinations, or ultimately to identify whether a destination is closed or not, and see if I want to go to a coffee shop. Maybe you will have some knowledge saying, oh, this coffee shop closed at 6 p.m. Maybe it is already 7 p.m. Maybe you'll have a suggestion on going to another coffee shop, which is maybe another Starbucks, saying, oh, probably you want to go to another Starbucks.
If there's no further question, maybe we can, it's also about the time. I think if you have further question or would like to discuss more, feel free to reach out to us by email, and also I think we are all available on GitHub as well. Feel free to send issues or pull requests, and we're looking forward to learning more from you as well, and hopefully to improve our package and also improve the research in this line further.
Thank you guys so much for coming.
Thank you.
Thanks, everyone.
Thank you guys for hosting this tutorial. Bye.